So now I'm going to talk about a somewhat different kind of spectra. Imagine you see a spectra that looks like this. It's like a rainbow. Imagine this is a rainbow. Nice and continuous, like you might see from a ceiling lamp, but with 4 black stripes. 4 specific bands have been taken out of this nice continuous rainbow. And you might also notice, these bands are in just the same places as the emission spectra we were just talking about. What is this? What could cause a spectra like this? Let's get into it. So, let's imagine that I have, here's a light bulb, it's just giving off light, and here's me over here. I'm looking at the light. But unbeknownst to me at first, is that between me and the light bulb is a cloud of dust. And this dust is all made, for the sake of simplicity, it's all made of one kind of atom. And so, if I were to look at the light here, I know that it would be like a white ceiling lamp, a nice continuum spectrum, all the colors. But what I actually see, the light that actually gets to me, that I actually see with my eyes and look at with my spectrograph, looks like this. So what happened here? Well, to figure that out, we're going to have to look at this same process as we did in the emission spectrum, but in a slightly different way. The same process happens, we just kind of change what we think about as being the important parts of it. And I'll explain what I mean by that. So let's make our atom again. Got the nucleus and the orbitals. And here we've got our electrons that we know and love from last segment. Now, here I just started off by just sort of saying that an electron absorbed a photon and didn't really go into any more detail about that. But there was something else important there. Something I kind of glossed over the first time, but I'm going to talk about now. If you recall, one of the important properties of orbitals is that electrons cannot be between orbitals ever. So what happens if you have a photon and it comes in and hits an electron, but the photon's energy would not get the electron to this orbital. It would maybe only get the electron up to here. What happens then? Well, I'll tell you what happens. The photon just goes right through. The electron cannot absorb this photon, because if it did, it would put it between orbitals. And it can't do that. The electron can never be between orbitals. So if this photon doesn't have the precise right energy to get this electron to this orbital, it's just going to pass through the electron, as if the electron wasn't even there. Right? The same applies for these. you know, it comes in, doesn't have the exact right energy to go for this orbital jump, same thing. So you could have a wide variety of different kinds of light coming through this atom. But most of that light is not going to be one of the exact right energies to cause an electron jump, because the light's energy has to exactly match the energy difference between two orbitals for that to happen. But maybe one does. Maybe this light is the exact right energy, and it causes an orbital jump. Now, what happens if I'm over here? The light bulb is over here. It's coming this way. These two colors, they pass through as if there was nothing there. But this one gets absorbed. So I don't see this color, which again, this color corresponds exactly to the energy of this electron orbital jump and jump back down, which I'll get to in a little bit, which is the same as, you know, up here. So this is why this kind of spectra has black lines in it that are in the exact same spots as the lone colored lines in the emission spectrum. Because these black lines and these emitted lines each correspond to the same electron orbital jumps. Now you might be thinking, but Cooper, didn't you say that when the electron jumps up to a higher state, it's always going to want to jump back down and emit its photon back out in the process to get rid of that energy? And the answer is yes. However, well, yeah, okay, you might think, if it's doing that, then shouldn't these lines get filled back in when that same kind of photon gets emitted when the electron jumps back down? But there's a reason that it's not, and that's because when the electron jumps back down and emits a photon to get rid of that energy, that photon can go in any direction, right? The direction it gets emitted in is essentially random. So it could go in any direction, and it's probably not going to go in the direction that my eye is in, right? So I'm not going to see that emitted photon if I'm looking at light that's coming from this direction. So the line remains unfilled. And this is called an absorption spectrum. Pretty nice. So, yeah, same process, but we're thinking more about the conditions surrounding it and what kind of light's going through, what kind of light is not. So, yeah, we've got emission spectra, absorption spectrum. Spectrum is like the singular of spectra. I kind of use them interchangeably sometimes, which is weird, and I shouldn't do it, but I do. Yeah. And then a continuum spectrum is like a rainbow. Doesn't have these specific lines in it. So yeah, I think that about covers light and spectra. I believe you're now, having seen all these videos, ready to do the assignment if you haven't. So, you know, go ahead and do it. Thanks.